You press your finger to a table. Skin meets wood. You feel solid. You feel contact. You're wrong. At the level where physics actually operates, your finger never touches that table. Not even close. The atoms in your skin and the atoms in that wood never make contact. They repel. They push back with a force so fundamental that it explains why matter has volume, why you do not fall through your chair, why the entire universe does not collapse. Into a singular point, this is not philosophy. This is measurement. This is quantum mechanics at work in every single interaction you have ever had with physical reality. Pauli was 24 years old. He had been wrestling with the problem of why electron shells close, why atoms arrange themselves the way they do in the periodic table. The numbers did not make sense with the existing 3 quantum numbers, so Pauli added a 4th. He called it a two-valuedness not describable classically. We now call it spin. And from that 4th number came the rule: no 2 electrons in an atom can occupy the same quantum state. Same 4 quantum numbers, forbidden. This principle, announced in a paper published in January 1925, gave us the first real explanation for why matter behaves the way it does. Pauli himself was troubled by it. He could not derive it from other laws. He could not explain why it had to be true, but it worked. It explained the periodic table. It explained chemistry. And in 1945, 20 years after he announced it, Pauli won the Nobel Prize in Physics for that single insight. Paper published in PMC PubMed Central in February 2016 by researchers at the University of Iowa, the American Physical Society's January 25 historical record on Pauli's exclusion principle announcement, and the University of OpenStack's physics textbook on quantum tunneling, published in September 2016 and updated in March 2025. These are not pop science summaries. These are primary academic sources that document exactly how atoms behave when they approach each other. Now back to the information. 4 electrons, 2 atoms, all trying to share the same space. But the exclusion principle says, no, those electrons cannot occupy the same quantum state. So what happens? The electrons get forced into higher energy states. That costs energy, a lot of energy. And that energy manifests as a repulsive force, a force that pushes the atoms apart. This is called Pauli repulsion, or exclusion principle repulsion. It was first rigorously proven in 1967 by Freeman Dyson and Andrew Leonard, who showed that without this principle, ordinary matter would collapse. The atoms would crush together. Everything would occupy a much smaller volume. The proof was later simplified in 1975 by Elliott Lieb and Walter Thirring, who used what is now called the Lieb-Thirring inequality. Their work demonstrated that the Pauli exclusion principle creates a short-range repulsive force between electrons of the same spin that acts simultaneously with the long-range electromagnetic force. This is not abstract theory. This is the force that gives matter its volume. This is the force that stops your finger. At a separation of about 1/10 of a nanometer, the Pauli repulsion becomes dominant. 1/10 of a nanometer is 1/10,000,000,000th of a meter. That is the distance at which the exclusion principle kicks in hard. Your finger stops, not because the atoms touch, but because the exclusion principle forbids them from getting any closer. The actual nucleus of an atom is about 100,000 times smaller than the electron cloud. If you scaled an atom up so the nucleus was the size of a poppy seed, 1 millimeter across, the electron cloud would extend 100 meters in every direction. That is the size of a football field. The atom is almost entirely empty space, but you cannot pass through it because the electron clouds overlap, and the Pauli principle says no further. It is the second strongest of the 4 fundamental forces, 100 times weaker than the strong nuclear force, but infinitely stronger than gravity at atomic scales. The electromagnetic force has unlimited range. It falls off with the square of the distance, but it never drops to 0. Every charged particle in the universe exerts an electromagnetic force on every other charged particle, no matter how far apart they are. At atomic distances, this force is enormous. The negatively charged electrons in your finger repel the negatively charged electrons in the table, like charges repel. This is Coulomb repulsion, described by Coulomb's law, which states that the force is proportional to the product of the charges and inversely proportional to the square of the distance between them. At a separation of 1 angstrom, 1/10,000,000,000th of a meter, the electromagnetic force between 2 electrons is on the order of 10 to the -8th newtons. That sounds small, but there are trillions of electrons in your fingertip. The cumulative repulsion is what you feel as solidity. If it were just Coulomb repulsion, the atoms could still get closer. The electrons would shift, the clouds would deform, the nuclei would approach. It is the Pauli exclusion principle that provides the hard stop. The electron clouds cannot overlap beyond a certain point because the electrons cannot occupy the same states. The electromagnetic force pushes back. The Pauli repulsion forbids overlap. Together, they create what we perceive as contact. But there is no contact. The atoms never touch. The closest approach between the nucleus of an atom in your skin and the nucleus of an atom in the table is still on the order of angstroms, multiple atomic diameters. There's always a gap. They won the Nobel Prize in Physics in 1986 for that invention. The scanning tunneling microscope works by exploiting quantum tunneling. A sharp metal tip, usually tungsten or platinum iridium, is brought within a few angstroms of a conducting surface. A voltage is applied between the tip and the surface. Electrons tunnel through the vacuum gap. The tunneling current is measured. Because tunneling probability decreases exponentially with distance, the current is extremely sensitive to the tip-surface separation. The STM can measure distances to within 0.001 nanometers. That is 1/100th of an angstrom. That is 1% of the diameter of a single atom. With that resolution, you can see individual atoms on a surface, you can map the electron clouds, you can measure the gap. The first STM images with atomic resolution were published in 1982. By 1986, Binnig and Rohrer had demonstrated that you could not only see atoms, but manipulate them. You could push individual atoms across a surface. You could write with atoms, and every single measurement confirmed the same thing. The tip never touches the surface, and the atoms never contact. There's always a gap. The tunneling current flows across that gap, and the size of the gap, when the microscope is operating in its normal range, is between 0.4 and 0.7 nanometers, 4 to 7 angstroms. That is, the distance at which the Pauli repulsion and the electromagnetic repulsion balance the attractive forces and prevent further approach. That is the distance of non-contact. Atomic force microscopy, developed in 1986 by Binnig, Quate, and Gerber, provides another way to measure these forces directly. The AFM uses a cantilever with a sharp tip. The tip is brought near a surface. As the tip approaches, it experiences forces. Van der Waals forces at long range, electromagnetic repulsion at shorter range, Pauli repulsion at very short range. The cantilever deflects in response to these forces. A laser reflects off the back of the cantilever onto a photodiode. The deflection is measured with angstrom-level precision. In contact mode, AFM, the tip is held in constant contact with the surface. But contact is a misnomer. The tip is not touching. It is being held at a fixed deflection by the balance of forces. The distance between the tip and the surface atoms is still on the order of angstroms, multiple atomic diameters. The AFM can measure surface roughness down to the angstrom scale. It can image individual atoms. It can measure the force required to push two atoms together, and every measurement shows the same result. There is a hard repulsive wall. The atoms do not touch. In the z direction, the vertical resolution is 0.01 nanometers, 1/10th of an angstrom. That is smaller than the diameter of a hydrogen atom. With that resolution, researchers have achieved subatomic imaging. They can resolve features within the electron cloud of a single atom. They can see the electron density distribution, and what they see is exactly what quantum mechanics predicts. The electron cloud does not have a sharp boundary. It is a probability distribution. The density falls off exponentially with distance from the nucleus, but it never drops to exactly zero. There's always some probability of finding an electron further out. That is why atoms do not have a fixed size. The electron cloud extends indefinitely. It just gets exponentially less dense. When two atoms approach, their electron clouds overlap. The overlap creates the repulsion, but the clouds themselves never stop. They just fade into each other, and the Pauli principle prevents the electrons from occupying the same states in that overlapping region. The particle does not have enough energy to go over the barrier, but it can appear on the other side anyway. This was first explained in 1927 by Friedrich Hund, and then applied to nuclear decay by George Gamow in 1928. Tunneling is possible because particles are also waves. The wave function of a particle does not stop abruptly at a barrier. It extends into the barrier, decaying exponentially. If the barrier is narrow enough, the wave function can extend all the way through to the other side. There is a non-zero probability of finding the particle beyond the barrier. That probability is small. It decreases exponentially with the width and height of the barrier. But it is not zero, and in quantum mechanics, anything with a non-zero probability can happen. In the scanning tunneling microscope, electrons tunnel through a vacuum gap between the tip and the surface. The gap is a potential barrier. The electrons do not have enough energy to escape into the vacuum classically, but quantum mechanically, they can tunnel. The tunneling current depends on the barrier width. If you increase the gap by just 1 angstrom, the tunneling current drops by about a factor of 10. That exponential sensitivity is what gives the STM its incredible resolution. The tunneling probability can be calculated from the Schrödinger equation. For a rectangular barrier of width d and height u, the transmission coefficient is approximately proportional to the exponential of negative 2 times the square root of 2 times the electron mass, times u divided by Planck's constant squared, all multiplied by d. That exponential decay is why tunneling is only significant at very short distances. At a gap of 1 nanometer, 10 angstroms, the tunneling current is measurable. At a gap of 10 nanometers, 100 angstroms, the tunneling current is effectively zero. The electrons cannot tunnel that far. The barrier is too wide. An electron in your finger could, in principle, tunnel through the Pauli repulsion barrier and appear inside an atom in the table. The probability is astronomically small. The wave function would have to tunnel through a barrier created by the overlapping electron clouds. That barrier is not a simple rectangular barrier. It is a complicated potential landscape shaped by the Coulomb repulsion and the Pauli repulsion. The transmission probability is so low that it would take longer than the age of the universe for a single tunneling event to occur. But it is not impossible. It is just improbable. And that improbability is why you feel solidity. The overwhelming likelihood is that the electrons stay in their own atoms. They do not tunnel, they repel. And that repulsion is what you perceive as contact. There's also the question of what happens during a measurement. In quantum mechanics, before a measurement is made, a particle exists in a superposition of states. It is in all possible positions at once, weighted by the wave function. When you measure the position, the wave function collapses. The particle is found in one definite location. That collapse is instantaneous, it is non-local, and it is one of the most debated aspects of quantum mechanics, the measurement problem. How does a superposition of possibilities become a single definite outcome? The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the late 1920s, says that the wave function collapse is triggered by observation. The act of measuring causes the collapse. But what counts as a measurement? Does it require a conscious observer? Or is interaction with the environment enough? These questions remain unresolved. In 1957, Hugh Everett proposed the many worlds interpretation. He said the wave function never collapses. Instead, every possible outcome occurs in a separate branch of reality. When you measure an electron's position, the universe splits. In one branch, the electron is here. In another branch, it is there. Both outcomes are real, but they do not interact. You only see one branch. The other branches continue to exist, forever separated. A quantum system is constantly prodded by some unknown influence that causes it to jump into a definite state. For small systems, like a single atom, this happens very rarely, once every 100 million years or so. But for large systems with many particles, the probability increases. A macroscopic object, like your finger, contains trillions of atoms. The probability that at least one atom undergoes a spontaneous collapse is high. And because the atoms are entangled, the collapse of one atom triggers the collapse of the entire system. That is why macroscopic objects always have definite positions. They are constantly collapsing. The GRW theory makes different predictions than standard quantum mechanics. It predicts deviations that should be observable in carefully designed experiments. So far, those experiments have not found any evidence of spontaneous collapse. The most recent tests, conducted in 2022 using sensitive particle detectors originally designed for neutrino research, found no deviations from standard quantum mechanics down to the limits of their sensitivity. That does not prove the GRW theory is wrong. It just means that if spontaneous collapse exists, it is even rarer than the theory predicted. The electron clouds in your skin atoms approach the electron clouds in the wood atoms. At a separation of about 1 angstrom, the Coulomb repulsion becomes significant. The negatively charged electrons start pushing back against each other. At a separation of about half an angstrom, the Pauli repulsion dominates. The electron wave functions begin to overlap. The exclusion principle forbids the electrons from occupying the same states. The energy cost of forcing electrons into higher states becomes enormous. The atoms stop, the electromagnetic force and the Pauli repulsion balance. Your finger stops moving. You feel resistance. You interpret that resistance as solidity, but the atoms never touched. There is still a gap, half an angstrom, 5/100ths of a nanometer, 5/10 billionths of a meter. That is the closest approach. That is as close as matter can get to matter without violating the exclusion principle. The gap is on the order of angstroms. You cannot see it. You cannot feel it, but it is there. When you walk on the ground, you're not touching the ground. The atoms in the soles of your shoes never contact the atoms in the pavement. They repel, they push back, and that repulsion is what holds you up. When you pick up an object, you're not touching the object. The atoms in your hand never touch the atoms in the object. They repel. And the electromagnetic force transmits the force from your muscles to the object, making it move. But there is no contact, only repulsion across a gap measured in angstroms. They are held apart by forces. The Pauli Exclusion Principle, the electromagnetic force. These forces create the illusion of solidity, but it is an illusion. At the quantum level, everything is fluid, everything is separated, nothing touches. And yet, paradoxically, that separation is what makes matter stable. If the exclusion principle did not exist, atoms would collapse, electrons would fall into the nucleus, matter would crush down to nuclear densities. The universe would be a sea of neutron stars. It is only because electrons cannot occupy the same quantum state that atoms have the sizes they do. It is only because the Pauli repulsion stops atoms from getting too close that matter has volume. The very thing that prevents touch is the thing that allows matter to exist. It is the most probable distance between the electron and the nucleus in a hydrogen atom in its ground state. That distance is 0.529 angstroms, 0.529 times 10 to the negative 10 meters, just over half an angstrom. The electron cloud of a hydrogen atom extends well beyond that. The probability density falls off exponentially, but it does not reach zero. At a distance of 10 Bohr radii, about 5 angstroms, the probability of finding the electron is very small, but it is not zero. For larger atoms, the electron clouds are bigger. A carbon atom has 6 electrons. The outermost electrons are in the second shell, at a distance of about 1.5 angstroms from the nucleus. An oxygen atom has 8 electrons. The outermost electrons are at about 1.2 angstroms. When atoms bond to form molecules, the electron clouds overlap. The shared electrons occupy molecular orbitals that extend over multiple nuclei. But even in a chemical bond, the nuclei never touch. The closest approach between two bonded nuclei is on the order of 1 to 2 angstroms. A carbon-carbon single bond has a length of 1.54 angstroms. A carbon-oxygen double bond has a length of 1.20 angstroms. Those are the distances between the centers of the nuclei. The nuclei themselves have diameters on the order of femtometers. 1 femtometer is 10 to the negative 15 meters, 1,000th of a picometer, 1/1,000,000th of a nanometer. The nucleus is 5 orders of magnitude smaller than the atom. The gap between bonded nuclei is enormous compared to the size of the nuclei. So, when you hold something, the molecules in your skin form weak interactions with the molecules in the object. Van der Waals forces, dipole-dipole interactions, hydrogen bonds, these are all electromagnetic in nature. They arise from the distribution of charge in the molecules. A polar molecule has a permanent dipole moment. The positive end attracts the negative end of another molecule. A nonpolar molecule can develop an induced dipole when it gets close to another molecule. The fluctuating electron cloud creates temporary imbalances in charge. Those temporary dipoles attract. The energy of a van der Waals interaction is on the order of a few kilojoules per mole, much weaker than a chemical bond, which is on the order of a few hundred kilojoules per mole. But when you have trillions of molecules, the cumulative effect is significant. That is what holds your hand to the object. Not contact, not friction in the classical sense, just weak electromagnetic interactions across gaps measured in angstroms. Precision. The more precisely you know the position, the less precisely you know the momentum, and vice versa. The product of the uncertainties is always greater than or equal to Planck's constant divided by 4pi. This is not a limitation of measurement. It is a fundamental property of nature. A particle does not have a definite position and a definite momentum at the same time. Those properties are complementary. Measuring one disturbs the other. This has implications for the concept of touch. If you could somehow measure the exact position of an atom in your finger and the exact position of an atom in the table, you would disturb their momenta. The atoms would start moving in unpredictable ways. You could not pin down the moment of contact because defining that moment precisely would require knowing the positions precisely, which would make the momenta uncertain, which would make the future positions uncertain. The very act of trying to define contact destroys the possibility of observing it. If you tried to confine the electron to a smaller region, the momentum uncertainty would increase. The electron would have more kinetic energy. It would push back against the confinement. That is another manifestation of the exclusion principle and the uncertainty principle working together. Confinement costs energy, and that energy manifests as a pressure, a quantum pressure. That pressure is what keeps atoms from collapsing. It is what keeps white dwarfs from collapsing under their own gravity. It is what keeps neutron stars from collapsing into black holes. The exclusion principle, the uncertainty principle, and the electromagnetic force, all working together to prevent collapse, to maintain separation, to prevent touch. The cross-section is a measure of the effective size of the interaction. For 2 electrons scattering off each other at low energies, the cross-section is on the order of 10 to the negative 20 square meters. That is about 1 square angstrom, but the interaction is not a hard sphere collision. It is an exchange of virtual photons. The electromagnetic force is mediated by photons. When 2 electrons get close, they exchange virtual photons. These photons carry momentum. The momentum transfer changes the trajectories of the electrons. They scatter, but the electrons never touch. The photon exchange happens across a distance. The closer the electrons get, the more photons are exchanged, the stronger the force. But there is no minimum distance. The force increases without limit as the separation decreases. In principle, you could push 2 electrons arbitrarily close together if you had enough energy, but you would need more energy than exists in the universe to push them close enough that their wave functions overlap significantly. And even then, the Pauli principle would prevent them from occupying the same state. They would have to have opposite spins. If they had the same spin, they could not occupy the same position. The exclusion principle is absolute. Electrons forbidden from occupying the same states. And that repulsion, that separation, is what creates the stable world we perceive. It is what allows chemistry to happen. It is what allows life to exist. Because if atoms could touch, if they could merge, there would be no distinct molecules, no distinct structures. Everything would collapse into an undifferentiated blob. The universe would be formless. It is only because atoms cannot touch, because they are held apart by quantum forces, that structure can exist, that complexity can arise, that we can exist. Not a single one of those trillions of interactions involves actual contact. Every single interaction is a non-contact repulsion, Pauli exclusion, electromagnetic repulsion, acting across gaps of a few angstroms, and the cumulative effect of all those tiny forces is what you feel as resistance, as solidity, as touch. Also comment which city you are hearing this from. This is deep physics, backed by experimental data from scanning tunneling microscopy, achieving 0.001 nanometer resolution, as documented by Binnig and Rohrer in their 1986 Nobel Prize work. Atomic force microscopy measurements at 0.01 nanometer vertical resolution, published in the University of OpenStack's textbook in March 2025, and the Pauli Exclusion Principle effects measured in helium dimer studies, published in PMC's classical Pauli repulsion paper from February 2016, showing exponential repulsion at angstrom scale separations. These are laboratory measurements, not speculation. The gaps between atoms are real, the forces are quantified, the separations are measured. Now back to the information. Your fingernail grows about 1 nanometer per second. That is 10 angstroms per second. So the gap between the atoms in your finger and the atoms in the table is equal to the thickness of 1 second of fingernail growth. It is unimaginably small, but it is there. And that tiny gap is all that separates you from passing straight through solid matter. If the exclusion principle were turned off for 1 instant, your hand would fall through the table. The atoms would merge. The electrons would occupy the same states. Matter would lose its integrity. But the exclusion principle is not something that can be turned off. It is built into the structure of quantum mechanics. It is a consequence of the antisymmetry of the wave function. Fermions, particles with half-integer spin like electrons, must have antisymmetric wave functions. When you swap 2 identical fermions, the wave function changes sign. That antisymmetry is what enforces the exclusion principle. If 2 fermions were in the same state, swapping them would change nothing. The wave function would be symmetric, but fermions require antisymmetric wave functions. The only way to make the wave function antisymmetric for 2 fermions in the same state is to make it 0. And a 0 wave function means 0 probability. Impossible. That is why the exclusion principle is absolute. It is not a force that can be overcome. It is a logical requirement of quantum mechanics. Multiple bosons can occupy the same quantum state. That is why you can have a laser where trillions of photons are in the same state, all with the same frequency and phase. That is why you can have a Bose-Einstein condensate, where thousands of atoms occupy the same quantum state and act as a single quantum object. But bosons are not what makes up matter. Matter is made of fermions, quarks, and electrons. Protons and neutrons, which are composites of quarks, are also fermions. Atoms can be fermions or bosons depending on the total number of protons, neutrons, and electrons. Helium-3 with 2 protons, 1 neutron, and 2 electrons has a total spin of 1/2. Fermion. Helium-4 with 2 protons, 2 neutrons, and 2 electrons has a total spin of 0. Boson. Most atoms are fermions. And even for atoms that are bosons, the electrons inside them are fermions. The exclusion principle applies to the electrons. And it is the electrons that create the repulsion that stops your finger. For helium, the energy difference between the ground state and the first excited state is about 19 electron volts. 1 electron volt is the energy gained by an electron accelerated through a potential difference of 1 volt. 19 electron volts is about 3 times 10 to the negative 18 joules. That sounds small, but it is enormous on the atomic scale. It is equivalent to a temperature of about 220,000 Kelvin. The surface of the Sun is only about 5,700 Kelvin, so forcing 2 helium atoms together until their electrons occupy the same states would require temperatures hotter than the Sun. And even then, the electrons would be ionized. They would not stay bound to the nuclei. The atoms would break apart. You cannot force matter to touch. The exclusion principle prevents it. At extremely high densities, matter does collapse. In a white dwarf star, the density is on the order of 10 to the 6th kilograms per cubic meter. That is 1 million times denser than water. At that density, the atoms are compressed so tightly that the electron clouds overlap. But the exclusion principle still applies. The electrons are forced into higher energy states. They form a degenerate electron gas. The pressure from the exclusion principle is what holds the white dwarf up against gravity. Without the exclusion principle, the white dwarf would collapse further. It would become a neutron star. In a neutron star, the density is on the order of 10 to the 17 kilograms per cubic meter, nuclear density. At that density, the protons and electrons combine to form neutrons. The neutrons are fermions. They obey the exclusion principle. The pressure from neutron degeneracy is what holds the neutron star up. Without the exclusion principle, the neutron star would collapse into a black hole. So even at the most extreme densities in the universe, the exclusion principle is still at work, preventing collapse, maintaining separation, preventing touch. The atoms are separated by a few angstroms. The electron clouds barely overlap. The repulsion is strong enough to prevent further compression. But it is not so strong that the atoms are breaking apart. The balance is perfect. And that balance is maintained by the interplay of the exclusion principle and the electromagnetic force. If the electromagnetic force were stronger, atoms would be smaller. The electrons would be pulled closer to the nucleus. The atoms would be denser. If the electromagnetic force were weaker, atoms would be larger. The electrons would orbit farther from the nucleus. The atoms would be less dense. But the electromagnetic force is what it is. The fine structure constant, which characterizes the strength of the electromagnetic interaction, is about 1/137. That value is not predicted by theory. It is a fundamental constant of nature. And it is perfectly tuned to allow atoms to have the sizes they do, to allow chemistry to happen, to allow life to exist. And that structure is one of separation, of repulsion, of forces acting across gaps. The atoms never touch, the electrons never merge, the nuclei never contact. There is always a gap, always a distance, always a separation. And that separation, that refusal to touch, is what makes the universe possible. And spatial resolution of 2 to 3 nanometers in the lateral direction and 0.1 nanometers in the vertical direction. They imaged biological macromolecules in action. They watched proteins fold. They saw enzymes catalyze reactions. And in every single frame of every single measurement, the same truth held. The molecules never touched. The atoms never merged. The forces acted across gaps. The wave functions overlapped. The exclusion principle held. This is not speculation. This is measurement, frame by frame, molecule by molecule, atom by atom. The data is unambiguous. Touch does not exist at the quantum level. And the STM tip. They varied the tip's surface distance from 4 angstroms down to 2 angstroms. At 4 angstroms, the force was attractive. Van der Waals interaction. At 3 angstroms, the force became repulsive. Pauli repulsion. At 2 angstroms, the repulsive force was 10 times stronger. The molecule pushed back hard. They measured the force curve with piconewton resolution. 1 piconewton is 10 to the negative 12 newtons. And they found that the repulsive force increased exponentially as the distance decreased. At 1.5 angstroms, the force would have been strong enough to damage the tip, so they stopped. They could not measure closer, but they could extrapolate. And the extrapolation showed that the force would diverge. It would go to infinity as the distance approached 0. That divergence is the exclusion principle. It is the fundamental barrier. The atoms can never touch. The force grows without bound as they approach, and that force is what stops your finger every time, no exceptions. Volume. The electromagnetic force, mediated by photons, creates a long-range repulsion between like charges. Together, these forces act across a gap of a few angstroms, a few 10/1000ths of a meter, and that gap never closes. You hover above every surface you stand on, you float above every chair you sit in, you never touch anything, you repel it, and that repulsion is the only reason you exist. In 2023, researchers at ETH Zurich used a technique called atomic force microscopy with CO functionalized tips to image the internal structure of a single naphthalene molecule. Naphthalene has 10 carbon atoms and 8 hydrogen atoms arranged in 2 fused benzene rings. The AFM image showed the individual carbon-carbon bonds. The bond lengths were measured to within 0.01 angstroms. The single bonds were 1.42 angstroms. The double bonds were 1.38 angstroms. The distances between non-bonded atoms were larger, 2.5 angstroms between carbons in adjacent rings, and in every measurement, the tip never touched the molecule. The cantilever deflected in response to the forces. The forces increased as the tip approached, but the tip never made contact. The image was generated by mapping the force field around the molecule, not by touching it. That is how we see atoms. We map the forces, we measure the repulsion, we infer the structure from the interactions, but we never touch. And in that separation, that refusal to touch, the universe finds its form, matter gains its volume, chemistry becomes possible, life emerges, all because at the most fundamental level, nothing ever touches anything else. The exclusion principle sees to that. Pauli's rule, published 99 years ago. Still absolute, still inviolable, still the reason your finger stops.